Hello, everyone. It's a great pleasure to be at this conference in this city. I'm going to tell you about a formal verification of Scala programs using a tool called Stainless that we've been building in the last couple of years in my research group at EPFL. And this is the aerial view of the EPFL campus. You can see here Lake Geneva and the Alps. Mont Blanc, and so computer science building is somewhere here. So I'll be essentially telling you about getting certain pieces of code right. And I certainly understand that not all of your code can be perfect. But I believe it's very important to know how to make some parts of your code perfect. And once we know how to do that, then we can also adjust the way we develop code. And a lot of what I'll be talking today actually resonates with the talk of John Hughes yesterday. And you will see that, the kinds of specifications that we write in our approach to formal verification are typically executable specifications that you can reuse also for property-based testing. And so the tool that we'll be using is called Stainless. And let me introduce the motivation for using such a tool through a metaphor. So suppose that you want to develop a software to achieve some goal, but your software may be somewhat buggy. So it's not quite ready to achieve this goal. Now, if you put some more effort to manual testing, it's appears somewhat more suitable for the goal. But of course, you shouldn't stop at manual testing. We have seen yesterday that if you apply automated testing with automatically generated tests from properties, then you can get much further. You can generate more tests than you would ever be able to practically write by hand. But today, my goal is to try to go one step further and get rid of those remaining bugs that might be left after you run property-driven testing. And so then, even though I must admit that already here it was pretty tempting to use our software, and maybe that's going to be the best solution overall when we have a large piece of code. For a certain piece of code, we can actually, it is already feasible to prove them entirely correct. So I'm going to use a very simple example of computing a list of differences between some initial list. So suppose you have some monthly balances in your account. And then from there, you want to compute the list that has the same first element, just the initial balance, but then subsequent elements just indicate the delta, the difference between the 2 months. So we have +1 going from the first to the second, and then going to the third, we have -6. So that's the list that we compute. Okay, so one way to think about it is that there are 2 processes here. One we can call diffs to compute these differences, and the other one we can call undiffs. Okay, so similarly, once we have the initial element and these differences, then we can compute the actual monthly balances by simply adding the difference to the previous element. So let's actually try to write down this undiff function first. And here it is. It's actually a one-line function using operation scan left on lists. So here's how scan left works. If you have a list of elements, and you give it some initial element z and a function f, then it computes the list that contains that initial element, and then it applies the function to initial element and the first element of your list, and then applies it combines it again with the second element of the list, and so on. And so once we have this scan left using the addition and initial element 0, we'll get a list that starts with 0. But we are not interested in this 0. We want the list that starts with that first element. So we are going to take the tail of that list, so something like this. Okay, so And that turns out to be a fine description of this inverse process. And if I write a manual test and apply undiff to this list, 101 and minus 6, we indeed get the list 100, and then 101, and 95. Okay, so now our goal is to define the diffs function itself, that if I were to give it 100, 101, and 95, would compute 100, 1, and minus 6. And more generally, the kind of inverse relationship that I would like to have is that if I apply diffs to L and then apply undiff, I'll get back to the same list. And that should hold for all possible values of L. Okay? And so here's actually a fine implementation. I'm sure you have already constructed something similar in your head. I have chosen here to write it out explicitly so as a recursive function. And so let's see why this hopefully makes sense. So let's take an example of this list. I'm denoting a list here with the concatenation operator and nil at the end. So we would like to map, for example, such a list to this list here. So we match on the list. If it's empty, or if it has only one element, we are going to return the same list. And then if we have some initial element, for example, 100, and the rest of the list that we'll denote by t, then we are going to recursively compute the differences in this list. And this is going to return in something like 101, and then the differences. And so that 101 is going to be h1. And so then we are going to put back the initial element h, and we are going to compute the difference between h1 and h. Okay, so this 101 minus 100 is going to be our difference. And then the rest already has computed differences, so that's t1. Okay, so that's our list. And I only have one case in this pattern match. I don't want to have any other cases. Okay, does that make sense? This function. So all my examples will be in Scala, but they should be fairly translatable to other functional languages. And so to indicate the fact that I would like this function to be an inverse of undiff, I will say that undiff of the result, this underscore in this context of ensuring indicates that that's the result returned by this function, should be the original input L. And this is something that you can write already in Scala, and this denotes a runtime assertion that applies to a given value. And we will be using it to indicate post conditions in a kind of design by contract. And now Scala is going to execute this at runtime. And we can then write some manual tests. So we can call this function with, for example, it's 3, 13, 23. It's going to give back 3, 10, and 10. And in fact, every time I run such a diffs, because of the ensuring, the Scala execution is going to also verify that, in fact, if I apply undiffs, I got back the original list. And if everything was fine, it's just going to keep quiet. And in the case when something would have gone wrong, it would complain and crash with a runtime exception. And of course, you should write more tests, and you shouldn't stop at a manual test. You should use quick check, like we have seen yesterday. But one question is, even with quick check, when will you stop? When should you stop, right? So will you ever be done, or will there always be some little pieces of dirt left in your code? Okay, so let's try to run this file through our tool, Stainless. It's going to be lots of things passing by the screen and going a bit fast, but I'm going to highlight the important ones. And so this is running with lots of instrumentation at the moment. But what's important is this. Okay, it says that there were total 23 proof obligations, and 23 of them were valid. Okay, well, they were all cached. That's why it ran a bit faster than normally, but it runs fast even without having been run before. So what just happened is that our tool generated, in this case, 23 formulas that imply correctness of this function for all inputs. And it then used its own reasoning steps, in particular unfolding of recursive functions, as well as encoding into the input of satisfiability modular theory solvers to prove all these formulas logically valid. Okay? And so that was essentially the entire input that we gave. That obviously it's a very small function, but I also wanted to emphasize that we did not need to give any additional hints. So there is some configuration file that you can set which solvers to use and which aspects of semantics you want to capture, but basically it works out of the box. Okay, so we get proof guarantees that are similar in terms of doing symbolic reasoning, doing proofs, like in proof assistants such as Coq and Isabelle, but in many cases we get more automation. And the specifications and code that we have used it was entirely executable, much like you would use for a property-driven testing. So let's see where these 23 proof obligations come from. And in fact, there should be really fewer. It depends a bit on the verification condition generator that you select. So, but among the main ones here is that function terminates for all possible inputs. And I'll hopefully talk about termination a bit later. The next one is that pattern matching is exhaustive. We have two pattern matching expressions here. And finally, the system has proven, actually, that when you apply these other recursive functions, or a function defined using another higher order combinator, then the result is back the original list. So we are basically showing the equivalence of the inverse relationship between two recursive functions. And we managed to prove that it holds for all possible values of lists. And so lists can be arbitrarily long. Let me just reflect briefly about the pattern matching here. This is something that you get for free without having to write some additional specifications, because typically you don't want pattern matching to be non-exhaustive. So you don't want to miss cases. And in fact, Scala compiler tries as much as it can, based on its type system, to prove that you have handled all the cases, but sometimes it has to be conservative, and sometimes it runs out of resources trying to check these conditions as well. So in the outermost pattern match, it should be hopefully straightforward that we have covered all the cases. We have the nil case. We have the case of list of length 1. Then we have this case, which handles all the other lists, right? But this case is a bit more interesting. Here, I pattern match, and I'm getting back a list, but I don't check for the case of nil. And that's why Scala compiler, when I compile this, issues a warning. It says, well, maybe you forgot to handle the nil case. But actually, our tool shows that it's not possible that you ever get nil here. Why would it not be possible to get nil as a result of this recursive call? So if you look at the function itself, right, you can see that when t is not nil, which it isn't because we have handled this case, then also we get that as another property, when diffs is called with a non-empty list, it also returns a non-empty list, right? So that's why. So the system looks into definitions of functions and unfolds them in order to establish properties like this. So in the rest of the talk, I'll try to talk about, highlight two aspects of working with such formal verification tool. One is how to get specifications. And it doesn't really work to order some and deliver them to your home. And the other one is about termination. Okay, so we have higher order functions here. And it turns out that even defining what I want in terms of termination is an interesting question. Okay, so let me discuss first where we might find specifications. Okay, so it turns out that specifications are around. We just need to be trained in finding them, like this truffle finding dog. And sometimes we get them for free. And so we've seen already examples of this phenomenon. Some of the specifications we get from program semantics. If we have a pattern matching, we would like it to be exhaustive. So that's one example. There are other cases that naturally arise. In Scala, you have head and tail defined on arbitrary lists. And then if you try to apply head or tail to an empty list, then you're going to get an exception. But you never really want to get such exception, right? That's a result of a coding error. And so we can statically check that such exceptions don't happen. Division by zero is another one that's typically considered too difficult to check statically, but you can emit verification conditions, and if when you manage to show them, then you'll be able to conclude that there's no possibility of division by zero. Of course, you can always explicitly check whether something is zero, and in that case, it will be easy for system to see that you have just checked that. And another example is indexing into collection. If you're using integers to index, then you don't want these integers to be negative, or when you have arrays to be too large. And so the great thing about all these kinds of properties is that you don't need to explicitly indicate that you want them checked. The system is going to generate proof obligations for them. So that's what I mean as the source of, the first source of specification that you get for free, basically program semantics and the notion of runtime errors. Now you can go a little bit further and say that you would like a bit stronger semantics that will allow you to check more errors. So I have just verified this program. On the other hand, you might argue that the program shouldn't have verified because I here have subtraction of ints. Now, if you come from Haskell, you would maybe think, what's the problem with subtracting to ints, right? In fact, int in Scala is a 32-bit signed integer. So we are working with 2's complement representation. We have modular arithmetic. And depending on what you want, this can be considered a fine thing to do. And in fact, in this case, even the inverse relationship holds. You subtract them, and sometimes it wraps around, but it wraps around in dual way when you put them together. On the other hand, there may be situations where you don't want, or you at least want to be warned about the possibility of such overflows and underflows. And so that's basically a choice that you can make if you're using our tool. And if you turn this option on, then the system for the program that we've seen actually finds the inputs for which there will be underflow during subtraction, or overflow, depending how you define it. So I can actually show you this here. So there is a strict arithmetic, which was set to false, because after all, Java semantics says that it's fine to do all these operations. The result is well defined. And so you could say that Scala semantics follows that one. And now we can nonetheless emit these warnings, because often people would like to use 32-bit numbers or 64-bit numbers for efficiency reasons, because the big ints are about 100 times slower in the Java implementation. And you would still want to be warned about these overflows. And so here you have found an error as a subtraction overflow. And if you scroll back, the counterexample is reported somewhere here. So here's a counterexample as a list with these two values. So when I was running this earlier, I got this particular value. It's mostly deterministic, but if you, it's sort of input dependent. So if you make small changes to the system, then the counterexample is reported change. And unfortunately, we don't have nice counterexample minimization that Quick Check has. That would be a nice feature here. So this particular input here, here you have a subtraction, so you need to compute 0 minus this number, and this number is minus 2 to the 31, which is just a bit too small to be able to be representable when you flip its sign. Okay, and that's why you get this error. So we may want to fix this error, and I was thinking, well, I should actually just work with increasing sequences. Let's try to look at this simpler case, and then I specified what it means for a sequence to be increasing, and I said that I require the input list to be, or sequence to be increasing. And here's the definition of increasing as a recursive function, right? So if I have 2 elements in this list, then the first one should be less than equal to the second one, and the rest of the list should be increasing. That's the kind of specification you would use for sorting, for example, as well. And so when you run this, then you get a counterexample. In fact, the previous counterexample was already an increasing sequence, but here I got another one, and I went and checked it. Apparently, I used GHCI to check that this made sense using arbitrary precision arithmetic, and indeed, 2 to the 31 is this number, and the subtraction of these 2 values that I got is a little bit bigger number. So there was an overflow. Then I tried to reproduce that indeed something different happens in Scala. So when I do minus on these assigned 32-bit integers, I get a negative number. This is not something that should be happening if these were unbounded integers. Then I tried to compute what is 2 to the 31, and I got 29. So for those who know Scala or Java, this is actually not exponentiation, right? So this is just a bit flipping operation. Okay, so then we still have a counterexample, but I would like to have a specification that really rules out counterexamples for these sequences. And so what I want actually is a sequence that starts with a number that's 0 or positive, and then continues as increasing. And here's how I specified it. So I said that either input list is nil, or its head is greater than or equal to 0, and then it's increasing. And when I run it with that, then everything verifies. Okay, so it establishes that there will be never any overflows and underflows here. Okay, and so to see why I never get again overflows or underflows, I actually need to know that these will continue to be all non-negative, and that when I subtract such non-negative numbers, then I won't have overflows or underflows. And so I need to look inside this recursive definition in order to be able to do that. And that's precisely what the system does. In fact, it uses a very simple strategy to unfold recursive functions. First, it doesn't unfold them, and then it unfolds them a little bit more, and then it unfolds all of them a little bit more, and so on. So if you have a lot of recursive calls and branching, this eventually generates, pretty quickly generates large formulas, and then you may be out of luck, but you actually capture a large part of input space in this bounded execution that is limited by how big formulas the solvers can handle. Okay, so we've discussed yesterday, I think, what happens if specifications are wrong. And this is sometimes, often this question comes up when people see all the effort that one needs to put in writing some of the specifications, and then you realize that, oh, but you could make mistake there, right? And of course, when you start writing specifications, you'll be more likely to make mistakes in specifications than in code itself, but that's fine. So what we are aiming for is simply to write specifications to be as independent of code, and therefore wrong as independently of code as possible. And then the probability of having two things that conform to each other, but both of them wrong in the same way, is actually much smaller than the probability of code itself being wrong. And there's a variety of ways of writing specifications, and that's what gives us freedom to really think about these properties differently than the efficiently executable code. So when I was actually going to write this first version of increasing sequence that is non-negative, I thought, I just need to handle the first element, and I just wrote here that the x should be greater than or equal to 0. And then to my surprise, I again got a counterexample. And so just as I was preparing this, I also made a mistake in specification. But then I was able to fix the specification, and then this version also works. So this is an alternative where I incorporate this non-negativeness as part of the definition of increasing. And this also proves correct. OK, so we've talked about two sources of free specifications, basically program semantics. And I've also introduced the preconditions that allow us to restrict the inputs to functions by, again, writing some properties of these inputs. Let me just quickly point out a very simple form of specifications that I like, because they can be used to illustrate what the function should do without coming up with some magical numbers in your examples. So in this Diffs example, if I take a list x1, x2, x3, and x4, the output should be x1, and then x2 minus x1, then x3 minus x2, and x4 minus x3. And to me, this actually really captures the essence of a function like that. Of course, it does it only for lists of length 4, but at least I don't need to come up with some hundreds and 95s and so on that really don't seem to have anything to do with the particular idea of the function. And the good thing is that the way our verifier works, once it unfolds functions about 4 times, then it's going to be able to either prove that this property holds or to disprove it. So you get predictability for these certain kinds of specifications. And so this also, in this case, it succeeds and it proves it. And here I have used the big int type, so unbounded integers, and which means that we have still proven it, even though we've done it only for a list of length 4, we've still proven it for infinitely many inputs. If you put int instead of big int, then you'll prove it for a large number, but finitely many inputs. And so both things work. OK, so let's now point out that we've seen already another natural source of specifications, which does require us to occasionally write some extra functions, but sometimes these functions are also available because we want to use them in our code itself. And this is the situation where we have inverse functions. So we have seen that diffs and undiff are inverse to each other, so we can use undiff to specify diffs, or conversely. And you can write the specification of undiff, a specification of diff by using undiff in post condition here, or the other way around, or you can write an external function check that we have seen before that just states the relationship. This affects a little bit how the proof is performed, because it's all based upon unfolding, and sometimes you may need to tell the system, do induction on the first argument. So there are many examples in practice that involve inverse functions. This includes compression and decompression. We've verified some simple examples of such functionality. Pretty printing and parsing, serialization and deserialization. Many file formats are essentially this kind of, so storing them and reconstructing them it has this inverse relationship, or should have this inverse relationship, and it's actually very buggy. I'm sure many of you have experienced the situation where something wrong happens when things are serialized or deserialized. And then, of course, there's something even simpler than if functions that are inverse to each other, which is that you have another function that does basically the same thing. And again, so I apologize that I'm repeating the same things that we have seen yesterday. But basically what I'm saying is, well, all these things you can use also to do formal verification. And what is surprising, it can work. And so here I have defined diffs2, which is, if you remember, our diffs function was recursively defined with this nested pattern matching. And here I'm defined diffs2 that just does some special cases to check for nil, and then uses zip with the function and its tail. So here's L, the whole list, and here's T, which is its tail. And so we know that if you want to compare two elements, you can zip the function with its tail, and then here I'm doing the difference. And this also works. You can prove that these two functions actually compute the same thing for every possible input list. And if you want to state it externally, then you can write this property that takes L as a parameter, because we prove always things for all possible L. And there's this keyword here, holds. It's really a shorthand for saying ensuring result is always true. Okay, so ensuring res is true. And here I give it a hint, do induction on the structural induction on L. Okay, so that's another source of specifications, and we mentioned, you saw examples that came in questions yesterday, where that if you have a previous version of your code and you made substantial changes, then you can do regression verification just like you do regression testing. Okay, another source of specification are MOOCs. So I'm basically just going to use an opportunity to present a kind of algebraic specification for a data structure. And it so happens that in this functional programming class that was taught as one of the first MOOCs in Europe by Martin Rodersky, so there were two classes, and in the second one, there's correctness of binary search tree storing integers that Martin proves manually, sort of demonstrating that equational reasoning functional programs works, and it's very convenient. And so here's the entire code of this binary search tree. It's similar to the one that we saw yesterday. It's a bit simpler because I don't have keys and values. I only have values. So it's really a set of these integers that I'm storing. And I have insertion into a tree that I call incl. And then I have contains, which tests whether an element is inside. And now these algebraic specifications, they would use observer methods. So contains is something that you can use to probe what is inside the data structure. And by probing with all possible inputs, you actually get to know what you should care about this data structure, right? This data structure is meant to represent a set of elements, and contains characterizes this set. And inclusion is then the operation that allows you to, starting from an empty set, build up any set you want, any finite set you want. Okay, so and here's what this lecture segment proves. It proves these three algebraic laws, that empty tree does not contain anything, so arbitrary element x is not included in empty tree, and that if you add an element into some set, then it's contained in it. And finally, if x and y are two different elements, then checking whether y is contained in this S union singleton x, basically, so in the tree where you added x. So what is that? X and y are distinct. Well, y will be inside this extended set if and only if it was in the original set, right? And this is actually algebraic characterization of the finite set. And so in this lecture, which I encourage you to look at if you can find access to it, because Coursera has been making it more and more difficult to watch these videos for free. So Martin shows using induction, structural induction, equational reasoning, and so function definitions and case analysis, that these properties indeed hold. And this presentation takes around 15 minutes for these 24 lines of code. And that's sort of the baseline for proofs, right? Manual proofs are baseline for proofs. And so if you write this using our system, so you write 20 lines of properties, and in some cases, the hint to prove them by recursion, by induction, and then it takes around a second for Stainless to prove them all, okay? So if you actually know why properties hold, then you can write this down, and it gets checked pretty fast. So also yesterday, we've heard about models as an example, a strategy of specifying things. A very impressive example of a model was the SEL4 microkernel development that team in NICTA, which is now Data61 in Australia, did, where they built several implementations of a microkernel. One of them was in C, that's the one that you run, and then related to it a Haskell implementation and an Isabelle interactive theorem prover implementation. They were all proven to conform to each other. So those are rather heavyweight models. There are much lighter versions of models. So by a model, I mean something that represents your original data in some possibly more abstract form. So you can take, like yesterday, a representation of a tree using a list. That's a great way of proving correctness of many data structures. A more abstract view would be multisets or sets, even more abstract. I like these ones because it turns out that you can automate reasoning about them very well, and they still capture a lot of sort of insertion, deletion, merging of structures, and so on. And even simpler thing you can do is to measure sizes of things. That's also very useful. Gives you an idea of whether you are losing something or not. And also, it can help establish other properties, because when you do this reasoning and constraint solving, you can sometimes conclude, oh, well, this thing is empty because it has size 0. And so that's a very powerful way to prune the search space in finding counterexamples. So in our Diffs example, because we already have a list, and there's nothing too interesting happening with the set of elements. In fact, just the one set is guaranteed to be, the first element is guaranteed to be preserved, and that's about it. But at least we know that we get the same size of the result. And we can write that, and it just works. So size of a list is defined in our library as a natural recursive function that is guarantees to return non-negative integer. And so these kinds of properties also work pretty well with this kind of verification approach, and they're quite useful. If you use set as a content, then you can also specify, for example, trees. That doesn't give you the sorting representation, but it gives you the description of the set of elements and how this changes when you perform some operation. So here's a simple binary search tree. Again, we're just storing some values that are, in this case, unbounded integers. And I can define the content of the tree as a set of these integers by just recursively computing the union of all elements. And then here's an invariant. Here's an example of just a function that returns Boolean, and that checks whether invariant is true. Now, actually, this one is not so great for one reason, which is that it uses a for all quantifier. And this is something that we are trying to move away from. But here you could replace it with executable for all, because you should just be traversing the set. So it's basically bounded quantifier over this set of elements. And it's just expressing the right kind of invariant. So this one should be really executable. It just happens to be written here as in this form of implication. And then what I really wanted to show is what a specification of insert looks like. So you say that input should be this binary search tree, which is just a function that I defined before. And then the output should, again, be binary search tree. Moreover, the result, as viewed as a set, and this is the function content that computes the set, should be content of the input tree extended with this new value. So a singleton set with this new value, and this is union. Okay, so that's a pretty good description of the insertion, I would say, even though it's only in terms of sets of values. And so this also works reasonably well. Okay, so I wanted to mention one more feature, which is relatively recent, which I think is important because it's a step towards encapsulating these properties in laws so that you get them at the place where you want them without doing too much work. And this is basically the way type classes should be, right? And in some Haskell extensions, I guess they can have these properties. And so I'm showing you how you can get these kinds of properties in Scala using the stainless verifier. So here I'm specifying just plain old algebraic monoids on no category theory here. So I have the neutral element called empty and the binary operation here called append on some domain A. But monoid is not just this, right? It's just this operation and the neutral element. It really is defined by the laws, and the laws say that empty is the left and right inverse, and that associativity holds. And we can write these as simply functions that return Booleans. I didn't indicate here, but the return type would be Boolean. It gets inferred. And then, if I want to say, here's a monoid, right? For example, big int with plus is a monoid. How do I say that? Well, I define, I create an instance, or I construct an object that extends this class. Here's using the kind of Java-like, Scala-like notation, new monoid of big int. And then I refine here the definition. So these are abstract methods here. So I define empty to be actual 0 over begins and append to be addition. And what happens behind the scenes is that when this is generated, all these properties are checked. Okay? So I don't have to write them every time. I just instantiate, and the system knows, okay, so all these properties should be checked. And then you can write that lists are monoid, or you can write the kind of instance declarations that lift one kind of structure into a structure on lists and so on. So the typical things that you can do with type classes, here you can do with in the presence of these laws that get checked for you as well. Okay, and then a great use of monoid that we have seen yesterday is that they have associativity. So if you have a collection that permits some divide and conquer operations, for example, fold, you may want to fold left and right and then combine the results. And you can require, well, I don't want just any operation, but I want operation that is a monoid. And in fact, I shouldn't be passing here f here. I should just be accessing f from the monoid itself. I'm sorry, that's a mistake. So this should be, f should go away, and I should just use m.append here inside. Sorry, that's a typo in the slide. Okay, so but the basic idea is that I package the operations together with the fact that they satisfy the right operations. And so I like in particular the scan that allows us to compute things such as the scan that we used in our list differences example. But if we had a very large collection, then we can do it in parallel, which is sort of a nice insight in these parallel divide and conquer algorithms. And this can be encapsulated in this higher order function. We can do this already, but now we can also do the checks that the function that we are passing is associative. And so when you do that, then it's also appropriate to verify such collections that allow divide and conquer algorithms. And Alexander Prokop, a student of Martin Odersky, has developed such a collection called conc-tree and conc-rope, and this was published in a conference on parallel computing. So one of my former PhD students, Ravikanda Madhavan, has verified correctness of this collection, and he also showed that you can use some instrumentation of the semantics to further describe and prove the bounds on the running time of these operations. So this was done in the previous version of our system that was called Leon, and reported in this Popple paper a couple of years back. Okay, so I know you're already wondering, when, will this ever stop? The second remark in my talk is about termination. I mentioned that Stainless automatically proves termination of functions. It turns out that the way it does it, it tries to infer measures on the arguments, typically lexicographic measures on sizes of these arguments. You can specify these using decreases clauses explicitly when system doesn't manage to do it, but in many cases it manages to do it. And so you can see, for example, here that we have pattern matched on L and obtained T. T is structurally, it's a shorter list than L, and we are calling, making recursive call on this shorter list, and that's the reason why this recursion terminates. So why do we want termination? In program analysis, often termination is not something that you explicitly aim to prove. You can define program semantics in a way that the termination is ignored and still have correct reasoning sort of treating termination as an orthogonal thing. Well, if you can prove termination, I would argue that it is a very good thing to do, because many functions, certainly internal functions, you would like to be terminating, and so you might as well know if something fishy is happening. There are other reasons that make it natural to prove termination when you want to use equational reasoning. If somebody writes a definition of a function, f of x is equal 1 plus f of x, then if you treat this as equality, f of x cancels and you get 0 equal 1. And typically, when we have a function definition, you would like to use it as an equation. And if somebody defines this thing and you use it as an equation, you have just added false in your assumption. Okay? So that just complicates matters. There are all kinds of things that you can do to alleviate that. You can tell users they shouldn't do that. You say, well, you define this function, that therefore you have just assumed false here, and I can prove whatever I want. But that's obviously not a very useful thing to do to your users. You can instead say that, well, you don't necessarily get an equation out of recursive function definition, right? That's just your intent, and then maybe you get it, maybe you don't. And so that makes things a bit more difficult then. Whenever you want to use an equation, then you need to prove some obligation at that point. Or you can do what used to be fashionable, I guess, in domain theory, and extend all your types with some bottom type. And then that means that something that you might think is either true or false may also be bottom, or something that you thought is 0, 1, or 2 may also be bottom, and so on. And this was popular in one of the original interactive proof assistants, LCF, but later people have moved on to working with total functions. And so if you look at more recent interactive proof assistants that reason about the properties, then formally, then you find that they use total functions. Now, of course, not all functions should be terminating. But if you have some function that interacts, some piece of code, I should say that interacts with the users, with the environment, they might well not be terminating. But then probably they will not be pure functions, right? So you will already be running them in some sort of monad if you look at it semantically. And then you might as well incorporate, model them semantically by adding some fuel parameters and an option type. So in that sense, you can recover the meaning of these functions in a system that requires termination. So for all these reasons, I think it's not a bad choice to require termination. Okay, so, but why is the question of termination interesting when you have higher order functions? So first of all, what does it mean? If I have a function such as pair map that takes a pair and some function f and then applies this function to first and the second element, this is what it does. So is this function always terminating, right? That's the kind of question we want to ask. Well, it's not always terminating. If f doesn't terminate, then of course the function is not going to terminate. But in some sense, it's not our fault, right? What else could you do if you take another function as an argument? If you're never going to apply it, it's not a very useful argument to take. So probably you're going to apply your functions as arguments. And so then the kind of property that you would like to have is that if you are given functions that terminate, then you will terminate yourself. But given that you can call functions in principle with themselves and so on, right? So just establishing how to what this termination criterion is might not be obvious. And so the solution, or one solution that we found appropriate, is to look at the type system frameworks. And in type system, there's a way to assign meaning to types. Here's just a function type from A to B. And you can say that's the space of the set of those terms such that for every argument in this argument type, when you look at this term f applied to that argument, then this term will evaluate infinitely many steps to some value that belongs to this result type, right? And so that's a kind of definition that captures, I would say, this intuition. And it's a definition that's that's essentially reducibility used in logic and type systems. And that's what we used in order to present a type theoretic foundation of Stainless, of our verification system. So we introduced a system that we modestly called system FR, where R can stand for recursion or refinement, because one of our goals was also to handle expressive forms of recursive data types. And so we have system F without kinds, and then the dependent types, so products, sums, unions, intersections, singletons, and so on. We have these refinement types that capture preconditions and postconditions, a bit like in liquid Haskell. In fact, not just a bit, but quite a bit like in liquid Haskell. So we can, in the type system itself, we can support reasoning about termination of streams and even contravariant recursive definitions. Now, to express these things at the surface language, we need some extra annotations for Scala, but for the kinds of positive data type definitions, you can use this type system to explain simpler type checking rules. And so our type checking also generates these proof obligations that ensure termination of all functions. So my postdoc, Jad Hamza, has formalized the soundness of this type system using proof assistant. Turned out to be 20,000 lines of code. And so we have then reworked this verification condition generator that generates proof obligations following this type system. And this is the recent UPSA paper. Okay, so and then with this, the state of the system is, the big picture is roughly as follows. So we use a Scala compiler, either mostly the old one. We have tried to use the new one, but the new one ran away from us. We didn't manage to catch up with it yet. So we have an old version of the front end as well. And then we really built our own trees and ran some sort of Hindley-Milner type inference on it. And then we run these additional refinement checks. And so there's these system FR rules on top of that that allow us to generate proof obligations. And then these proof obligations are given to a solver that Nicola Vorol in our group built that unfolds these recursive functions and then encodes the certain constructs into first order language of these SMT solvers. SMT solvers are these theorem provers that are good at reasoning not just about equality and functions, but also about integers, algebraic data types, and so on. And so as I mentioned, we have measure inference, and we have our own little compiler and an interpreter inside for validating counterexamples and things like this. Okay, so we've tried it on some code that we wrote ourselves, various benchmarks we've accumulated over the past couple of years. Around 14,000 lines of code verifies in around 6.5 minutes. And so they're the kinds of examples that I have mentioned before. I mentioned compression, data structure. A lot of our bigger examples are data structures. We have tried to map some solidity contracts into models in terms of these pure functions. There's a verification challenge to build a kind of key servers with which we made some progress in verifying this. And you can formalize parts of mathematics as well if you want. Okay, so then we use it in the formal verification course, and then we have been collaborating with some blockchain-related companies that are interested in distributed algorithms. At some point, we spoke to IOHK, which I was under the impression that they used it for some parts of their Scala code base, but I don't know exactly the situation right now. And we are interested in extending this technique to other languages, so if you would like to adapt it to other front ends. We also have a parsing combinator library that my student, PhD student Roma Edelman recently built, which makes it very convenient to write parsers with syntax tree constructions and that, using parsing combinators that run fairly efficiently. And so this should be make it possible to adapt it to other front ends. Now, I should mention that it's very tempting once you have such expressive system to say we can formalize all kinds of mathematical properties. But it's worthwhile keeping in mind that we have a kind of top type that in Scala is called any. And we have this kind of subtyping relationship. So the function space from any to any is subtype of any. And that's sort of what you would expect from something that includes all types. But this is not something you would expect in set theory if these were total functions, right? And of course, the answer is that these are not total functions. At best, you should think of them as computable functions, or in reality, really, our proof talks about terms, so sets of terms. And so if you really want to somehow have mathematical properties that then talk about your computable functions, then maybe you should just use something that's meant for mathematics. And that can be something like a Coq proof assistant or Isabelle proof assistant. Coq would be convenient because we already have embedding of our system in there. But also, maybe another possibility is set theory, which can be used to carry out the soundness proof and to therefore embed system FR as well. And when it comes to formalized set theory, I thought it would be interesting to observe that one of the most developed and earliest systems for formalized set theory is called Mizar, and it was developed by Andrei Tribulets, who was born in 1941 in Krakow. Okay, and so this system that we have built is primarily work of Nicolas Voirol, with important contribution by Roman Rucci and Jad Hamza. And it builds on the previous system we had, Leon, that did not just verification, but also synthesis. And so we could kind of step back to try to make a more practically usable system. But the example of Diffs actually comes from the synthesis benchmark, where you have the specification of undiff function, and you're asking the system, can you construct the diffs function that is the inverse? And this actually seems to still work. We had this online demo where you can do specification, and the system gives you in the web IDE the counterexamples and so on. And you can then also ask it to solve synthesis and repair problems. And here it's searching. It takes just a little bit longer, because as you can imagine, verification is a very expensive process, and the most techniques that are used in this syntax-based synthesis, they enumerate lots of terms, so you sort of add one more exponential on top of verification, and that's why you get sometimes significant running times even to construct some simple examples. But if we are lucky, then why is it going forwards and backwards? It has a search tree, and then it's measuring how much it has explored given what it knows is there. So, but what it knows also changes, and that's why it's going forwards and backwards. Shouldn't be for too long. It's actually even using input-output examples to filter out things, so it's not always just trying to verify. If it gets counterexamples for previous failed things, then it's going to try these counterexamples by execution. And so I don't claim that this represents state-of-the-art of synthesis, maybe from a couple of years back, but maybe, hopefully not today. It does finish, though. Yes.
Do you have a question?
I just thought, oops.
The examples that you showed for the verification were all fully functional, very well-written functions. But if you look in the Scala standard library, a lot of the very basic functions are very imperative. Can the system be used actually to verify the Scala standard library? Because it's written in a very imperative style?
We have our own standard library, so, and one of the reasons is that the original standard library wasn't written as a purely functional purely functional one, and also because the encoding into SMT solvers does not mesh so well with subtyping. So we have some support for sort of the kind of Scala form of subtyping to model it within the domain of SMT solvers. We sort of inject various the universe of types into some simple general purpose type. And so that has some costs in terms of reasoning. So if you stay in kind of more ML-like subset, you get better results in terms of performance and verification. And that's one of the reasons, as well as the lack of guarantees about purity, that we don't really work with the standard library as it is. Also, yeah, so there are other reasons as well. Currently, there are some additional features that we don't support. So our language actually also prevents null pointers by null reference by construction. So you simply cannot create nulls and so on. We support some form of state in the system, but it's a similar, it's a sort of linear type-like restriction, so that we don't have to encode the general heap. So it was intentional design decision.
Yes, please. Two questions. One is, I have seen in your specification that you use Scala programs. Then is there any clean distinction between the specification and the implementation language? This is one question.
Sorry, I didn't understand this question.
Yes, the question is, what kind of things can you write in your specification? Because I have seen that there is not clean distinction between the specification and implementation.
So you can write, in principle, arbitrary executable specifications. So you are not restricted if you write purely functional code with integers, algebraic data types, and so on. But there are certain things that will be supported better by the solvers, like primitive operations on bit vectors and on integers. If you use multiplication of integers that are unbounded, then this is not guaranteed to be efficiently solvable or solvable at all using SMT solvers. But in principle, we map everything, and then we may run into limitations of the solvers that may time out.
Okay.
And the second question you had as well. The second question?
We can take this maybe offline.
Sure. Yes, sorry about that. Okay. So actually, I just had the concluding slide. I wanted to emphasize that this executable specification should be convenient for developers. You can reuse them for property-based testing or for verification. They also map, they have good guarantees in terms of finding counterexamples and finding proofs. And you can encode many things. I mentioned just now that there are certain imperative features we can encode. We have shown that you can model certain resource bounds, verification of resource bounds. And I think overall it's an interesting, working with these executable specifications as recursive pure functions is an interesting design point. Okay, so that's all I had. Thank you.
Thank you.